Hello there, and welcome to The Ancient Historian, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we begin a journey not forward, but backward, far backward into a realm so strange, so mysterious, that even the stars have not yet appeared. Our focus tonight is a time before time, long before people, long before planets, long before even the faintest flicker of galaxies. We're going to explore a question that feels as vast and impossible as the night sky itself. What was there before the universe? If this kind of quiet, wandering question stirs your curiosity, I'd love to hear from you. Drop a comment below and share where you're watching from, and what time it is there right now. It's incredible to imagine people all over the world, each following this journey through time together, like scattered sparks tracing the edges of history. If you feel drawn in, tap like or subscribe. It helps this little signal ripple outward, reaching other curious souls moving through the world like shadows chasing sunlight. No pressure. Think of it as a soft invitation, like a drifting feather settling on a hidden path, or the faintest whisper of a story carried on the wind, guiding us somewhere strange, secret, and entirely unexpected. So settle back, let your mind wander, and follow this thread wherever it leads. Imagine the universe as we know it, a swirling expanse of stars, galaxies, light, and cosmic dust. Now, gently strip it away, piece by piece, until nothing remains. No galaxies, no stars, no atoms, no space, no time. What's left? The silence before the first note of a song? The blank page before the first word of a story? Or something far stranger, something we cannot imagine, yet which still somehow existed, waiting in the wings? For most of human history, questions like this lived only in myths and stories. Ancient cultures tried to answer them through creation tales, where gods, serpents, or cosmic eggs burst forth to shape the world. In Hindu traditions, the universe emerged from cycles of creation and destruction, stretching back infinitely. In Greek philosophy, thinkers wondered if chaos and endless void came first, before order emerged. Even the Norse imagined a yawning gap, Ginnungagap, out of which worlds eventually formed. These stories gave shape to the unimaginable. What was before the universe? But then came science. In the early 20th century, astronomers peered into the night sky and discovered something astonishing. The universe was not static, but expanding. Galaxies were rushing away from us in all directions, as if space itself was stretching. This led to the idea of the Big Bang, the theory that everything we know exploded out of an unimaginably small, dense point some 13.8 billion years ago. Yet here lies the mystery. If the Big Bang was the beginning, then what came before it? Was there a before at all? Some scientists argue that asking what came before the universe is like asking what's north of the North Pole. Time itself, they say, began with the Big Bang. Before that, there was no before. No ticking clock, no flowing seconds, no past or future. Just nothing, though not the kind of nothing we can imagine. Not empty space. Not a blank canvas. Not a dark void. Because even space itself, the stage on which reality unfolds, did not yet exist. But others wonder if that's the whole story. What if our universe is just one bubble in an infinite frothing sea of universes? Some physicists call this the multiverse. In this picture, our universe could have budded off from another, like a droplet forming on the edge of a wave. If so, there might have been something before the Big Bang, another universe, older, stranger, that set the stage for ours. Another idea is the cyclic model. The universe may have no true beginning, but instead expands, collapses, and is reborn over and over, like a cosmic heartbeat. If that's true, then what came before our Big Bang was not nothingness, but another universe collapsing in on itself, only to ignite again in a fiery rebirth. An eternal cycle with no first moment, no final end. And then there's the quantum realm, the strange world of probabilities, uncertainty and invisible fields. Some scientists suggest that before the universe, there was a quantum vacuum, not empty, but seething with potential. Out of that restless nothingness, a tiny fluctuation could have sparked the Big Bang. In this view, nothingness itself is unstable, always bubbling, always capable of giving birth to something. But perhaps the most haunting possibility is that the question itself has no answer. That the human mind, evolved to count seasons, follow rivers, and measure days, is simply not equipped to grasp what before the universe means. Our words before, after, nothing, something fall apart when we push them too far. And yet, it is precisely in this place of mystery, at the edge of what we can understand, that wonder grows. Think of it this way. When you look up at the night sky, you're not just seeing stars. You're seeing the story of the universe unfolding backward in time. Light from the nearest star left 4 years ago. Light from distant galaxies left billions of years ago. The deeper you look, the further back in time you travel. Eventually, telescopes like the James Webb pierce so far that they nearly touch the dawn of time itself. Beyond that silence, mystery, a horizon our minds cannot yet cross. And so, here we are, balanced between myth and science, between story and silence, wondering what if anything came before at all. Close your eyes for a moment and drift backward through time. Backward past your childhood, past the centuries of human history, past the rise of civilizations and the shaping of continents, past the age of the dinosaurs, the forming of mountains, the cooling of the earth, past the birth of the sun itself. Keep going, farther still, until everything you know, every star, every atom, every breath, begins to dissolve. The night sky is no longer filled with constellations. The galaxies scatter into nothing. And before you, there is only darkness, infinite, stretching in all directions. A silence so complete that it is beyond silence. A void so vast it swallows even the thought of time. But then, in this endless nothingness, something stirs. Not a sound, not a shape, but a pulse, a tremor of possibility. For in the heart of what seems like nothing lies the potential for everything. Scientists call this moment a singularity, a point smaller than the tip of a pin, yet dense with all the energy, all the matter, and all the laws that would govern the universe to come. Imagine the weight of billions upon billions of galaxies compressed into a space no bigger than a grain of sand. No stars yet. No light yet. Only pure potential waiting. Then an instant of unimaginable transformation. A burst not like any explosion you could picture, but an expansion of space itself. The universe begins not with fire, but with stretching. In less than a fraction of a second, it balloons outward at speeds beyond comprehension. This is the event we call the Big Bang, though it was not truly a bang in the way we understand. It was not sound, for sound requires air. And there was no air. It was creation, raw and absolute. A universe inflating, unfolding, racing outward from that singular point. Temperature soars to extremes our minds can barely imagine. Trillions of degrees. The newborn universe is a sea of blinding energy, a storm of radiation, seething, boiling, churning with particles bursting into existence and vanishing again in the blink of an eye. Quarks, electrons, neutrinos fleeting, unstable, colliding endlessly in a cosmic dance. The first seconds of the universe are chaos incarnate. A roiling storm where matter and antimatter annihilate each other. And yet, against all odds, a tiny imbalance remains. Just enough matter survives to one day form galaxies, stars, and the very atoms of your body. And as the universe expands, it cools. Still violent, still furious, but cooling. From inconceivable heat to something slightly less hostile, energy begins to slow. Particles that once could not exist without being torn apart now find stability. Quarks bind together into protons and neutrons. These are the seeds, the building blocks of everything that will ever be. In the first 3 minutes, the universe begins to weave the simplest elements. Hydrogen, helium, and trace whispers of lithium. There are no heavy elements yet, no carbon, no oxygen, no iron. Those will come much later in the hearts of stars. But here, at the dawn of creation, the first ingredients are stirred into existence. Imagine yourself floating in this newborn cosmos. There are no planets, no galaxies, no shining suns. Only a vast, expanding ocean of glowing plasma, too hot and too dense to let light travel freely. The universe is bright, but it is a brightness trapped, scattered endlessly by the particles within. If you could open your eyes here, you would see nothing but a blinding fog stretching in all directions. It is a universe in waiting, a canvas not yet revealed. Hundreds of thousands of years pass. Expansion continues. Cooling continues. The energy storm softens. The plasma sea begins to thin. For the first time, true atoms can form. Electrons settle into orbits around protons. And suddenly, the universe changes forever. The fog lifts. Light is freed. The cosmos becomes transparent. The first light, born of this moment, still lingers today. We call it the cosmic microwave background. A faint echo of that primordial dawn, whispering across space. A ghostly afterglow of the universe's earliest memory. From this clarity, the great architecture of the cosmos begins to take shape. Gravity, the quiet sculptor, begins its slow work. Invisible threads of attraction tug matter into vast webs, gathering clouds of gas across light years, drawing them into knots, into spheres, into the first stars. These stars ignite, fusing hydrogen into helium, burning with a brilliance never before seen. Their light pierces the cosmic darkness, ending the long night. In their fiery hearts, heavier elements are forged: carbon, oxygen, nitrogen, the raw materials of life. When they die, these stars scatter their treasures across space, enriching the void, preparing the way for planets, for oceans, for beings who one day would look back and wonder how it all began. But in these earliest ages, the universe is still wild, still chaotic. Galaxies collide, stars are born and die in violent bursts. Black holes form, anchoring the centers of galaxies, pulling in gas and dust, shaping the cosmos with invisible force. The universe, once a silent void, is now alive with light and energy, a symphony of creation playing out over billions of years. And yet, beneath the roaring of quasars, the spinning of galaxies, the collapse of stars, there remains the faint memory of that first moment. The singularity, the point of origin, from absolute nothing to everything, from silence to a universe filled with sound and light and possibility. Every breath you take, every atom in your body, every star in the night sky can trace its ancestry back to that instant, that spark, that unfathomable birth. The universe is still expanding today, racing outward into the unknown. Galaxies drift farther apart. Stars burn and die. New stars are born. The story that began in that first flash continues, and we, tiny observers on a pale blue planet, are part of its unfolding. We carry the dust of stars in our veins, the memory of the cosmos in our cells. And as we look back across billions of years, to the very first seconds, we are reminded that everything, the vastness of the universe, the smallest grain of sand, the thoughts in your mind once emerged from nothing. Picture yourself drifting into a space where even the idea of space hasn't yet arrived. No stars, no galaxies, no planets, no dust swirling in cosmic currents. Not even the cold darkness we imagine when thinking of outer space, because even darkness implies the presence of space in which it lingers. Before the universe as we know it, there was a silence deeper than anything we've ever touched, a kind of vastness that wasn't vast, because vast itself is a measurement, and measurements require beginnings and endings. Here, there were none. Some ancient cultures gave this silence a name. In Hindu philosophy, it was sometimes called the pralaya, a state of cosmic rest, a long breath drawn inward before the next creation was exhaled. In Greek thought, philosophers spoke of chaos, not chaos as in disorder, but chaos as in pure, yawning openness, an undefined realm waiting to be shaped. Even the Norse told stories of Ginnungagap, the gaping void that existed before fire and ice met to form the first spark of being. In these myths, the silence was not emptiness, it was a womb. But when we shift from myth to science, the silence sharpens into something stranger still. Physicists don't picture a vast, empty blackness before the universe. Instead, they describe a reality where our everyday language fails. Before the universe, there may not have been a before at all, because time itself had not yet been born. Imagine trying to ask what happened before the first tick of a clock. The question itself tangles, because without time, before has no anchor. Here's where the mind starts to stumble and wander into paradox. In one sense, there was no before, and yet, in another, physicists imagine strange possibilities hidden beneath that first moment of expansion we call the Big Bang. Some suggest a quantum foam, a seething field of tiny fluctuations that never rest. These fluctuations are like whispers, flickering in and out of existence, sparking probabilities instead of certainties. Perhaps one of those fluctuations inflated wildly, unfolding into what became our universe. Others imagine an endless cycle universe is born, expanding, cooling, collapsing, and then sparking again. If so, our universe may be just the latest in an infinite chain of creations and dissolutions, each new reality woven from the ashes of the last. The silence before creation may not have been silence at all, but the faint pulse of an older cosmos collapsing into itself. And then there are theories of the multiverse, where countless universes blossom like bubbles in an infinite sea, each bubble expanding with its own laws of physics, its own possibilities, perhaps its own versions of time. In this view, before our universe wasn't nothing, it was everything. A vast and eternal ocean from which universes rise and fade like waves. Yet, strangely, even science circles back to an idea that feels almost poetic. At the smallest scales of reality, particles blur into probabilities, appearing and disappearing in the blink of nothing. In this realm, silence is never still. Even in the supposed void, there is restless possibility. Could it be that the nothing before the universe was not empty at all, but full of potential, full of sparks waiting to ignite, full of hidden patterns yet to unfold? Now close your eyes and imagine this silence, stretching not just for years, not just for billions of years, but for a span where years themselves have no meaning. Imagine a stillness so complete that even the concept of stillness does not yet exist. No winds, no seas, no fire, no sky, no matter, no time. A realm that is not a realm. A shadow of what might be, before the light of creation poured forth. And yet, through that silence, came the first tremor, the first unfolding, The first great rush of energy, what we call the Big Bang, may have been less of a bang and more of a blooming, like a flower opening from the soil of nothingness. And perhaps that blooming was always waiting there, hidden in the silence before creation, like a secret melody, humming beneath an untuned instrument, waiting for the first note to be struck. Now let your mind drift deeper, beyond even the first tremor of creation, beyond the faintest whisper of the Big Bang. Step into a realm where the very ideas of time and space have no meaning. We try to imagine it using clocks and rulers, seconds and meters, that all of those are inventions that depend on the universe existing. Without space, there is no distance. Without time, there is no duration. Without matter, there is nothing to measure. And yet, somehow, something existed, or at least the potential for everything. Think about time as a river. Normally, it flows from past to future, carrying events like leaves floating on a current. But before the universe, there was no river. No past, no future, not even a trickle. Just a vast, incomprehensible stillness. Physicists sometimes describe this as a state where classical laws break down, where causality, the simple idea that one thing causes another, does not apply. Imagine asking why in such a state. The question has no meaning because why assumes a chain of events. And yet, it is precisely in this mind-bending boundary that the story of everything begins. Some scientists turn to quantum physics for a glimpse into this realm. At the tiniest scales, reality behaves unlike anything in our everyday world. Particles can exist in multiple states at once. They can pop in and out of existence. There are fluctuations, tiny blips of energy, that appear and disappear in a cosmic dance without pattern or time. Some propose that these fluctuations could have triggered the birth of our universe, that the Big Bang was not a singular beginning, but the outcome of a small nudge in an infinite quantum field, a whisper in a vast, silent ocean of potential. Others ask if our universe is just one bubble in a cosmic foam, part of a multiverse. Perhaps before our universe, there were countless other universes, each with its own rules, expanding and collapsing, invisible to us, leaving no trace but the faint echoes of possibility. If so, then, before, the universe is not a single point of nothing, but a sea of hidden realities, each shaping what comes next in ways we cannot perceive. Now consider space itself. We are accustomed to imagining emptiness as black, as a stage on which stars appear. But before the universe, there was no stage. Space was not even a concept yet. No width, no height, no depth. Only the seeds of what could one day be. In a strange sense, the universe did not expand into space. It created space as it expanded. Every inch of distance we observe today was woven from the fabric of creation itself, born in the first heartbeat of existence. And yet, even with all this, some mysteries remain so deep that they brush against poetry. Could the nothingness before the universe have been eternal? Could it have existed forever? A quiet, hidden ocean of infinite potential, waiting, patient, for the first spark. Or is forever itself meaningless, because time had not yet begun? As you picture this, try to imagine witnessing creation from the outside, not as an observer within time, but as a thought floating outside the universe, beyond the reach of clocks, calendars, and light itself. The laws we know, gravity, motion, even mathematics as we understand it, did not yet apply. The universe was not written yet. It was a blank page, waiting for the first stroke of reality. And in that blankness, the first possibilities stirred. The tiniest fluctuations in energy, the faintest hints of instability, the seeds of something emerging from nothing. The cosmos began to take shape, but not instantly. For a long time, what emerged was chaotic, unpredictable, and breathtakingly strange. Galaxies, stars, and matter as we know them were not yet formed. Instead, there were forces, invisible threads tugging at what would one day become the fabric of reality, weaving an intricate pattern before we could even begin to perceive it. Now, let's drift into the realm where imagination begins to stretch beyond anything we experience in daily life. The quantum sea. This is the domain of the very small, the invisible scaffolding of reality, where particles blink in and out of existence and energy dances like flickering light across a stage that does not yet exist. Before the universe, it is thought that something akin to this quantum foam existed, a restless, trembling field where possibilities stirred in silence. In this quantum sea, nothing is not truly nothing. It is a bubbling, shifting space of potential, like the surface of a calm lake hiding undercurrents of immense power. Tiny fluctuations imperceptible to our senses can spark entire realities. A nudge here, a wave there, and suddenly, in one fraction of a second, the energy concentrates, inflates, and unfolds into what we eventually call the Big Bang. It is a universe born not from chaos or design, but from probability itself. Physicists imagine this quantum nothingness as a place where the rules of classical physics are irrelevant. In our world, cause and effect are reliable. A stone falls, a fire burns, a planet orbits. But in the quantum sea before time and space, these rules do not apply. A particle may exist in two places at once, or nowhere at all. An event can occur without a past, and yet still influence a future that has not yet begun. To step into this reality with your mind is to experience wonder, vertigo, and awe simultaneously. Some suggest that this quantum field is eternal, stretching beyond comprehension. Imagine an infinite, invisible ocean, restless but calm, silent yet humming with latent energy. Out of this quantum sea, universes may emerge like bubbles forming on a pond. Each bubble is a potential reality, growing, expanding, perhaps collapsing, or maybe enduring forever. Our universe could be one of countless others, each shaped by slight variations in the foam, each containing its own laws, its own time, its own reality. And yet, this field is far from static. Even in the absence of time, change can occur in ways that are difficult to grasp. Probabilities shift. Tiny fluctuations occur spontaneously. Energy moves and twists in ways beyond our understanding. It is as if the universe itself, before it existed, was alive with restless potential, vibrating with the faint echoes of creation yet to come. Now imagine witnessing this. There are no stars, no light, no dimensions. Yet, if you could see, you would observe an endless dance, subtle and intricate, almost imperceptible. A ballet of possibility that stretches beyond imagination. Some regions might stir more energetically, while others remain quiet, waiting. And from this trembling, one day a spark emerges. That spark is not random in the sense we understand it. It is the first heartbeat of reality. It inflates, expands, and begins to shape the structures that will eventually become space, time, and matter. In the first fractions of a second, the universe is a storm of energy, so intense that even light cannot travel freely. Particles flash into existence and vanish again, colliding, combining, and breaking apart in a primordial symphony. And yet, amid this apparent chaos, an order begins to emerge. Gravity, a force that does not yet have form, begins to sculpt the energy into the first structures. Patterns appear, like waves forming in a restless ocean. The seeds of galaxies, stars, and planets are planted, not as solid objects, but as concentrations of energy that will one day give rise to the tangible universe we know. The quantum sea continues to ripple, even as the universe begins to stretch and cool. Each fluctuation, each minuscule movement leaves an imprint, a faint echo that will influence the unfolding cosmos for billions of years. In a sense, the universe carries within it the memory of that restless, invisible ocean, the quantum foam from which it was born, shaping everything from the largest galaxy to the smallest particle in ways we are only beginning to understand. Now, let's drift even closer to the moment when the universe begins to take shape, when pure energy begins to crystallize into the building blocks of everything we know. From the restless quantum sea and the initial spark of the Big Bang, the cosmos evolves into a storm of unimaginable intensity. Temperatures soar to trillions of degrees, so hot that matter cannot yet exist in any stable form. Protons, neutrons, and electrons are constantly forming and dissolving in the furious plasma. This is a universe of motion, of collision, of relentless transformation. In this seething chaos, the first particles begin to stabilize. Quarks, which had existed only fleetingly, now combine to form protons and neutrons, creating the first tangible elements. Within minutes, hydrogen, helium, and trace amounts of lithium appear. These simple atoms are the seeds of everything that will follow. Imagine billions of these tiny particles swirling, colliding, and binding together, setting the stage for galaxies, stars, planets, and life itself. As matter forms, the universe continues to expand. Space itself stretches, carrying atoms along like driftwood on an invisible river. This expansion cools the cosmos, but it remains turbulent. Clouds of primordial gas ripple with gravitational forces, forming concentrations that will eventually give rise to stars. And in this turbulent sea, the first light begins to escape a glow that will echo across time as the cosmic microwave background. This is the whisper of creation, a faint glow that tells us about the earliest moments of existence. Picture yourself floating among these newborn particles. You cannot see them individually, they are too small, but you can feel the energy, the constant motion, the sense that something extraordinary is forming. This is a universe learning to exist, discovering the patterns that will govern galaxies, solar systems, and planets. Gravity begins to weave its invisible threads, pulling matter together, creating clumps that will eventually ignite nuclear fusion and birth the first stars. In this time, every particle, every collision, every tiny fluctuation carries infinite possibility. A single variation could alter the entire course of the cosmos. If the first atoms had formed slightly differently, or if the balance of forces had shifted, stars might never ignite, galaxies might never coalesce, and planets, including our own, would never exist. It is humbling to realize that the universe we inhabit is the result of countless infinitesimal events, happening in precise alignment over billions of years. And as the universe cools further, matter begins to organize on larger scales. Hydrogen clouds form vast filaments, stretching across unimaginable distances. Gravity pulls these filaments into knots, seeding the formation of protogalaxies. Inside these structures, dense regions collapse to ignite the first stars, and these stars, in their fiery furnaces, begin creating heavier elements, carbon, oxygen, nitrogen elements that will eventually become the building blocks of planets and life. Imagine this scene as if you are a silent witness. You drift past the first clouds of hydrogen, feel the pull of gravity shaping unseen patterns, hear the hum of energy coalescing into form. The universe is not quiet, it is alive with motion, with transformation, with the relentless emergence of order from chaos. It is in this crucible that the cosmos learns its laws, discovers its structure, and begins the journey that will ultimately lead to galaxies, planets, and beings capable of asking the question, what came before it all? Even in these earliest moments, there is elegance hidden. Patterns emerge from randomness. Forces balance each other, allowing structures to grow. The universe is teaching itself to exist, using the fundamental laws of physics as its guide. And every atom, every particle, every spark of energy carries within it a memory of this violent, formative time. A memory that stretches across billions of years to reach us today. Now imagine drifting through the universe as it begins to organize itself on a grand scale. The first atoms, hydrogen and helium, are everywhere, stretching across incomprehensible distances. Gravity, the invisible sculptor, tugs at these clouds, pulling denser regions together. Tiny fluctuations in density, almost imperceptible, become the seeds for something extraordinary. The first stars. These protostars are forming in silence, yet within them lies the power to illuminate a dark cosmos. Inside these dense clouds, hydrogen begins to collapse under gravity, heating as it compresses. Temperatures rise until nuclear fusion ignites, the force that powers stars. For the first time, the universe produces light in a concentrated, coherent way. This is starlight, a cosmic glow that will travel for billions of years, carrying the story of creation across space. Imagine witnessing this light for the very first time. A brilliance born from the sheer pressure and heat of collapsing gas. The first sign of structure emerging from chaos. The first stars are giants, far larger and more luminous than most stars we see today. Their lifespans are brief in cosmic terms, yet their influence is immense. These early stars forge heavier elements in their cores. Carbon, oxygen, nitrogen, and beyond. When they die in explosive supernova, they scatter these elements across space, seeding the universe with the raw materials for planets, for water, for life itself. Each star is a crucible, a forge that transforms simple atoms into the complex elements that will one day form worlds. As clusters of stars form, galaxies begin to emerge. Gravity pulls stars together into swirls and spirals, knots and filaments, creating the first galactic structures. These early galaxies are chaotic, colliding and merging. Yet through this turbulence comes order. Within these galaxies, stars continue to burn, die, and recycle their elements, shaping the chemistry of the cosmos. Picture yourself floating through these early galaxies, watching light scatter across space, witnessing matter condense into form, and feeling the hum of energy that underlies all creation. Even in this epoch, the universe is dynamic, unpredictable, and alive. Black holes form in the centers of nascent galaxies, pulling in matter with invisible hands. Jets of energy burst from these black holes, shaping the galaxies around them. Gas clouds swirl, collide, and compress. Patterns emerge from the chaos, and over millions of years, the vast structures of the universe, the cosmic web, begin to take shape. Consider the implications of this moment. Without these first stars, without their nuclear furnaces, the universe would remain a barren expanse of hydrogen and helium. No heavier elements could form, no planets, no chemistry for life. The universe as we know it owes its complexity to these first cosmic forges. Their light piercing the darkness, their death scattering the seeds of all future worlds. And yet, amid this activity, the universe continues to expand. Space stretches, carrying galaxies apart, shaping the large-scale structure of the cosmos. Gravity continues its subtle work, tugging and weaving, creating vast clusters and superclusters of galaxies. Each interaction, each collision, each burst of energy leaves its mark on the cosmos, shaping the environment in which future stars, planets, and life will emerge. Floating through this young universe, one can almost feel its heartbeat. The rhythm of creation pulses through every star, every cloud of gas, every flicker of light. It is a symphony that began in the quantum foam before time, and now, billions of years later, manifests as the dazzling architecture of the cosmos. Stars burn, collapse, scatter elements, and light the path for the endless unfolding of the universe. The first stars, in all their brilliance and impermanence, are the ancestors of everything we see in the night sky. Their light travels across time, a bridge connecting the universe's earliest moments to the present. Each photon is a messenger from the dawn of creation, whispering the story of the cosmos as it continues to expand, evolve, and unfold. Now imagine drifting through the universe, billions of years after the first stars ignited. The light of those early stars has traveled vast distances, illuminating a cosmos still in its youth. The universe is expanding, yet gravity continues to weave its invisible threads, gathering stars, gas, and dark matter into enormous structures. These are the first galaxies, immense islands of light in a vast, stretching ocean of space. Galaxies begin as collections of stars and gas, clumping together through gravity. Some take the shape of irregular blobs, chaotic and turbulent, while others start to spin, forming disks that will one day resemble the spirals we see today. Within these galaxies, stars continue to form, burn, and die, enriching the galactic environment with heavier elements. These elements will later become the raw material for planets, for life, and for the very fabric of everything that will emerge in the universe. Dark matter, invisible yet powerful, plays a crucial role in shaping these structures. It provides a gravitational scaffold, holding galaxies together even as they spin and collide. Without it, these islands of stars would fly apart, unable to maintain cohesion. Picture vast, invisible webs of dark matter stretching across the cosmos, guiding the formation of galaxies like an unseen hand, shaping the universe in ways we can sense but never see directly. Galactic collisions are frequent in these early times. Entire galaxies slam into one another, their stars rarely colliding but their gas clouds igniting massive bursts of star formation. These interactions are violent and transformative, creating new structures and triggering waves of activity that ripple across millions of light years. Imagine the shockwaves of energy spreading through interstellar space, compressing gas, igniting stars, and shaping the destiny of entire galaxies. Within each galaxy, star clusters form, supernovas scatter heavy elements, and black holes anchor the centers of these massive systems. Some black holes grow to enormous sizes, millions or even billions of times the mass of our sun, their gravity shaping the motion of stars around them. Jets of energy erupt from these black holes, carving cavities in surrounding gas and regulating the growth of their host galaxies. It is a universe alive with motion, energy, and the interplay of forces on a cosmic scale. Consider the variety of galaxies that emerge. Some are spirals, graceful and rotating, with arms curling outward like cosmic whirlpools. Others are ellipticals, smooth and massive, filled with ancient stars. Irregular galaxies defy classification, chaotic in structure, but full of raw potential. Each galaxy carries within it a story of formation, collision, and transformation, a unique history shaped by gravity, energy, and time. The large-scale structure of the universe begins to take shape as galaxies cluster together, forming filaments, walls, and voids. These vast structures stretch across hundreds of millions of light years, creating a cosmic web that defines the architecture of the universe. Gravity continues to sculpt this web, pulling galaxies into groups and clusters, shaping the environment in which future stars, planets, and life will emerge. Within this cosmic landscape, individual stars continue to evolve. Some explode as supernova, seeding their surroundings with heavy elements. Others form planetary systems, laying the groundwork for worlds like our own. And throughout it all, light travels across space, carrying information, energy, and the history of creation to every corner of the universe. Imagine observing this unfolding from a distance. The universe is no longer a chaotic sea of particles and energy. It is structured, organized, alive with dynamic processes. Galaxies spin, collide, and grow, each a self-contained system yet connected through gravity and the cosmic web. The universe has moved from a newborn, glowing plasma to a complex network of stars, gas, and dark matter, setting the stage for the countless wonders that will follow. And yet the universe is still expanding, stretching these galactic islands ever farther apart. Space itself is growing, carrying galaxies along invisible currents, shaping the large-scale structure in ways that continue even today. The cosmos is a living tapestry, constantly evolving, with galaxies as its vibrant threads, each one telling a story billions of years in the making. Now, let's shift our gaze from galaxies to the smaller, yet equally astonishing, scale of planetary systems. Within these spinning islands of stars, clouds of gas and dust swirl in vast rotating disks. These protoplanetary disks are the nurseries of planets, where gravity, collisions, and angular momentum conspire to transform microscopic grains into enormous worlds. Imagine floating within one of these disks, watching particles collide, stick together, and grow, forming the seeds of entire solar systems. Tiny dust grains, barely larger than specks of smoke, begin to clump together. Electrostatic forces cause them to stick, forming pebbles, then rocks, then kilometer-sized planetesimals. Gravity takes over, pulling these planetesimals together, creating protoplanets, early worlds that will eventually carve out orbits around their parent stars. Picture a chaotic dance of material, spinning faster and faster, forming rings, spirals, and clusters, all working together to build planets from raw cosmic matter. Meanwhile, the central star continues to shine, its nuclear furnace providing heat and energy. This energy shapes the surrounding disk, vaporizing some materials and allowing others to condense. In the cooler outer regions, ices and volatile compounds form, giving birth to gas giants and icy worlds. Closer to the star, rocky planets take shape, small at first, but growing steadily as they collide with other protoplanets. Each collision is a violent, transformative event, reshaping the emerging worlds and adding new layers of complexity. Some planetary systems are calm, evolving slowly over millions of years. Others are turbulent, with giant collisions sending shockwaves through the disk, scattering debris and triggering waves of new formation. This is a process of both destruction and creation. The chaos is necessary. Without it, planets would never form, and the intricate architecture of a solar system could not exist. Imagine the raw energy of these collisions, the flashes of heat, the formation of craters and mountains, the early sculpting of planetary surfaces. Within these forming systems, other processes are at work. Heavy elements, forged in the cores of the first stars and scattered by supernova, are incorporated into the protoplanets. These elements, carbon, oxygen, nitrogen, iron, silicon, will eventually create the complex chemistry necessary for atmospheres, oceans, and perhaps life. In this way, each planetary system carries within it the echoes of long-dead stars, connecting the birth of worlds to the larger cosmic story. As planets grow, their gravity influences the surrounding disk, shepherding smaller bodies, clearing paths, and capturing moons. Giant planets can migrate, reshaping the architecture of the system, flinging smaller worlds into new orbits or ejecting them entirely. The process is unpredictable, yet guided by the subtle, invisible hand of physics. Imagine watching these protoplanets interact, colliding, spinning, and dancing in a chaotic yet beautifully orchestrated cosmic ballet. Over millions of years, these planetary systems stabilize. Planets settle into their orbits, moons are captured, rings may form and dissipate, and the disks of gas and dust thin. What was once a chaotic swirl becomes a structured, dynamic system, a miniature cosmos within a galaxy. Each system unique, yet following the same universal rules of physics. Some systems will harbor rocky planets, some gas giants, and some, by chance, conditions conducive to the emergence of oceans, atmospheres, and eventually life. And all of this is happening against the backdrop of a universe that is still expanding, still evolving. Galaxies collide, stars ignite and die, supernovas scatter elements into space, and yet within these enormous processes, the delicate formation of planetary systems unfolds. Every planet, every moon, every asteroid is a product of forces billions of years in the making, a testament to the extraordinary complexity and interconnectedness of the cosmos. Picture yourself drifting among these emerging worlds, feeling the subtle tug of gravity, watching clouds of gas swirl, witnessing collisions that forge new surfaces, and imagining the immense span of time that stretches before them. From tiny grains of dust to planets that may one day harbor life, this is the slow, awe-inspiring creation of worlds, the universe taking shape on a scale we can almost grasp, yet remains far beyond our full comprehension. Now, let us zoom in closer, beyond stars and planets, into the intricate dance of molecules and energy that sets the stage for everything that might one day be considered alive. Even before life as we know it, the universe is already a vast chemical laboratory, teeming with interactions, reactions, and possibilities. Imagine floating through the space between young planets, drifting through clouds of gas, dust, and ice, where radiation from nearby stars ignites chemical transformations that will ripple through time. In these primordial environments, simple atoms like hydrogen, carbon, oxygen, and nitrogen collide and bond, forming increasingly complex molecules. Water molecules coalesce in icy grains. Organic molecules arise from the interplay of carbon and nitrogen. And amino acids, the very precursors to proteins, begin to appear. Each molecule is a tiny marvel, a product of chance and the fundamental laws of chemistry, forming spontaneously under conditions that may seem hostile, but are perfect for creativity on a cosmic scale. Consider the energy involved. Ultraviolet radiation from young stars bombards these molecules, breaking some apart while stimulating the formation of new, more complex compounds. Cosmic rays pierce the clouds, providing yet another source of energy for chemical reactions. Shockwaves from supernovas sweep through nearby space, compressing clouds, heating dust, and triggering bursts of chemical activity. It is chaotic, violent, and yet profoundly generative. Out of this turbulence, the universe begins to weave the threads of potential life. Within these early planetary environments, surfaces of dust grains and icy mantles act as catalysts. They bring molecules together, providing a stage for reactions that might not occur in free-floating space. Chemical bonds form, break, and reform, gradually increasing the complexity of molecules. Imagine clusters of carbon-based compounds growing, interacting, and assembling into structures that hint at the first steps toward life. The universe is sculpting possibilities with patience and precision, molecule by molecule, reaction by reaction. At the same time, gases like methane, ammonia, and carbon dioxide mix in young planetary atmospheres, creating additional opportunities for chemical evolution. Lightning strikes, volcanic activity, and ultraviolet radiation all play a part, driving reactions that produce new compounds and distribute them across nascent planets. These chemical pathways are the building blocks of biochemistry, establishing the potential for future biological systems. long before life itself ever emerges. Even in the vast darkness of interstellar space, complex chemistry unfolds. Molecules form in cold molecular clouds, drifting for millions of years before becoming incorporated into new stars and planetary systems. Comets and asteroids carry these molecules across space, delivering them to planetary surfaces, scattering the seeds of chemistry that could one day lead to life. Imagine each icy body as a tiny courier, transporting organic compounds across unimaginable distances, linking regions of the cosmos in a subtle chemical web. As planets cool and stabilize, oceans and atmospheres begin to develop, providing liquid water and energy sources necessary for further chemical evolution. Hydrothermal vents, shallow pools, and mineral-rich surfaces offer diverse environments where molecules can interact in increasingly complex ways. Each environment provides unique conditions, allowing reactions to proceed along different pathways, diversifying the chemical inventory of young worlds. Think about the scale of time involved. Millions of years pass as molecules form, recombine, and accumulate. Every collision, every reaction, every photon absorbed contributes to an evolving chemical landscape, setting the stage for life billions of years later. These are processes that occur invisibly, silently. They form the foundation for everything that will emerge in the cosmos. In this way, the universe is not merely a collection of stars and planets. It is an ongoing experiment in complexity. Atoms combine into molecules, molecules into networks, and networks into systems capable of transformation. Each step builds upon the last, guided by fundamental physical and chemical laws, and every environment contributes its own unique influence. This is the quiet, persistent artistry of the cosmos, unfolding over eons in ways both subtle and profound. And as these chemical foundations stabilize across planets and moons, the universe remains alive with energy and possibility. The ingredients for life are in place, but the spark, whatever it may be, has yet to ignite. Molecules float, interact, and evolve, a vast orchestra of matter and energy playing a prelude to something extraordinary, a story that will continue to unfold over billions of years, reaching toward the eventual emergence of living systems. Now, let's zoom further into the worlds themselves, exploring the places where chemistry and planetary conditions converge to create prebiotic environments, the potential cradles for life. Imagine a young planet, still forming, with oceans just beginning to settle, volcanic landscapes emitting clouds of steam and gases, and lightning streaking across turbulent skies. These early environments are dynamic, energetic, and chaotic. Yet within that chaos, patterns emerge that could support the first steps toward life. On these primordial planets, shallow pools and tidal zones provide a perfect laboratory for chemical reactions. Molecules washed ashore by early waves concentrate in small pockets, interacting in ways impossible in the open ocean. Sunlight and heat drive energy into these compounds, stimulating the formation of more complex structures. Think of each ripple of water as a subtle agent of organization, stirring molecules into configurations that edge ever closer to the structures necessary for life. Deep beneath the ocean's surface, hydrothermal vents spew mineral-rich water, creating stark contrasts of temperature and chemistry. Here, energy flows in abundance, and unique chemical gradients offer the potential for reactions that could not occur elsewhere. These vents are teeming not with life yet, but with possibility, a furnace where prebiotic chemistry can flourish, shielded from the extremes of surface conditions. Imagine the dramatic currents and rising plumes of minerals, each particle a participant in an intricate chemical ballet, pushing matter toward complexity. Meanwhile, meteorites and comets continue to deliver fresh materials from space. Organic molecules, amino acids, and simple sugars embedded in these icy bodies crash onto planetary surfaces, adding new ingredients to the prebiotic soup. Each impact is both destructive and creative, mixing existing compounds, generating heat, and spreading matter across the landscape. The universe itself becomes a provider of materials, connecting distant regions through cosmic delivery systems that shape the chemical potential of emerging planets. On land, volcanic activity and flowing lava shape the surfaces of young worlds, creating diverse microenvironments. Pools of water heated by volcanic energy may concentrate molecules, while the cooling lava forms mineral-rich surfaces where chemistry can proceed in unique ways. Pockets of concentrated elements, iron, sulfur, phosphorus, offer catalysts that may drive increasingly complex reactions, setting the stage for the formation of polymers and primitive structures that hint at life's potential. The role of energy in these environments cannot be overstated. Ultraviolet light from nearby stars, heat from geological activity, chemical gradients from hydrothermal vents, and even electrical discharges from storms all inject energy into these systems. Each source provides opportunities for molecules to interact, bond, and evolve. These energy inputs act like invisible hands guiding reactions, selecting for stability, complexity, and organization. Consider the diversity of possible planetary environments. Some planets may be dominated by oceans, others by vast deserts or volcanic plains. Some may have thick atmospheres trapping heat, while others remain cold and icy. Each setting offers different conditions for chemistry to unfold, creating countless experiments running in parallel across the cosmos. In this way, the universe explores potential pathways toward life on a scale far beyond human imagination. Time, as always, plays a critical role. Millions of years pass with cycles of heating and cooling, wetting and drying, collisions and quiescence. Molecules are tested over and over again, with some persisting, others breaking apart, and new structures emerging from the interplay. The prebiotic environment is patient, enduring, allowing complexity to accumulate slowly, subtly, yet inexorably, across eons. Even in these earliest conditions, hints of order begin to appear. Simple molecules link into chains, small reactions give rise to networks, and energy flows create gradients that may one day support the first metabolic processes. Each element, each compound, each environmental factor contributes to a web of potential, a tapestry of chemical possibilities that could, given the right spark, become the foundations of life. Imagine being a silent observer, drifting through these ancient worlds, feeling the subtle currents, seeing molecules dance in pools and clouds, witnessing impacts and lightning strikes, and sensing the quiet, persistent shaping of the environment. This is a universe in preparation, setting the stage, arranging the pieces for a story that will unfold across billions of years, connecting the chaos of matter with the eventual emergence of life. Now, let us move even closer to the threshold between chemistry and biology, to a time when the first self-replicating molecules may have emerged. Picture a primordial environment, pools of warm liquid teeming with complex molecules, each jostling for space, energy, and opportunity. Among them, some molecules possess a remarkable property. They can make copies of themselves, creating patterns that persist across time. This is the earliest whisper of life, the first echo of biology emerging from pure chemistry. These molecules, possibly RNA or simple precursors, operate according to the rules of chemistry. Yet their ability to replicate introduces something fundamentally new. Patterns can now persist, evolve, and interact. Some molecules are more stable, others replicate faster, and over countless cycles, a primitive form of selection begins. Imagine this process not as a sudden spark, but as a slow, delicate unfolding, a chemical dance where structure and function emerge almost imperceptibly. Energy continues to flow through these systems, from heat, radiation, and chemical gradients. Each energy input nudges molecules into new configurations, breaking old bonds and forming new ones. Collisions, shifts in temperature, and interactions with minerals or water surfaces provide opportunities for molecules to stabilize, fold, and link into chains capable of carrying information. Picture the subtle complexity. Millions of molecules interacting, competing, and cooperating, each a tiny participant in an epic story spanning eons. In these primordial pools, the environment itself plays a crucial role. Wetting and drying cycles, temperature fluctuations, and mineral surfaces catalyze reactions, allowing molecules to assemble in ways impossible in open space. These conditions may create the first proto-metabolic systems, where energy flows begin to be harnessed in organized ways. It is the universe experimenting, trying out chemical pathways, setting the stage for systems capable of persistence and adaptation. As self-replicating molecules proliferate, interactions become increasingly complex. Some molecules form protective shells, perhaps enclosing themselves in primitive compartments. Others develop simple catalytic functions, accelerating reactions that benefit their own replication. It is a nascent ecosystem at the molecular level, a microscopic world of competition, cooperation, and innovation, all occurring long before life as we recognize it emerges. Imagine these molecules as the first storytellers of biology. Each replication cycle is a narrative of survival, persistence, and adaptation. Every stable molecule that survives another cycle carries its pattern forward, contributing to a growing diversity of molecular forms. The story is not yet life in the biological sense, but it is the blueprint, the experiment that will one day produce cells, organisms, and eventually, consciousness. External forces continue to shape this unfolding drama. Meteor impacts deliver new molecules. Heat events rearrange chemical landscapes, and radiation stimulates new reactions. Each event, each fluctuation offers opportunities for innovation, introducing variability that can lead to more complex molecular systems. The environment is both a challenge and a partner, a dynamic force that drives chemical evolution forward. Over countless generations of molecular replication, networks begin to form. Molecules interact, catalyze each other's formation, and create rudimentary cycles resembling metabolism. It is a delicate balance, fragile yet persistent, where stability and change coexist. Imagine observing this microscopic world, seeing patterns emerge from chaos, witnessing the first steps toward organized systems capable of growth and adaptation. Even at this early stage, the principles that will govern biology are already present. Information is stored and transmitted, energy is harnessed, and complexity accumulates. These self-replicating molecules are not life yet, but they carry the potential for life, serving as the bridge between chemistry and the biological systems that will eventually dominate our planet. Drifting through this ancient molecular landscape, one can feel the profound significance of these events. From random collisions and chemical reactions emerges the possibility of persistence, a pathway toward self-sustaining systems, and the first echoes of life's enduring presence. It is here, at the molecular level, that the story of life begins, quietly, invisibly, yet with consequences that will reverberate across billions of years. Now, imagine the microscopic stage we have already entered, where self-replicating molecules float and interact within primordial pools and chemical-rich environments. Among these molecules, some begin to associate within protective boundaries, forming the earliest protocells. These are not yet full-fledged cells, but tiny compartments that separate internal chemistry from the surrounding environment, creating the first microcosms capable of organizing reactions and preserving information. Protocells are fascinating because they introduce spatial organization. Within their simple lipid membranes, molecules can concentrate, interact more efficiently, and establish rudimentary networks resembling metabolism. Imagine droplets of fatty molecules in warm pools of water, assembling spontaneously into spheres, encapsulating RNA-like strands and other chemical machinery. These tiny spheres provide a stage for chemical interactions to occur in isolation, allowing certain patterns to persist and evolve. The environment remains a critical player. Wet-dry cycles, heat gradients, mineral surfaces, and the influx of new molecules from meteorites all influence protocell formation. Each protocell is subjected to a test of stability. Some dissolve, others persist, and a few replicate by budding or splitting. Those that endure set the foundation for increasingly complex structures. Picture a universe at the microscopic level, full of these fragile, fleeting droplets, each a miniature experiment in life's first architecture. Energy continues to flow through these protocells in subtle ways. Thermal gradients, chemical reactions, and even light can influence their behavior. Encapsulated molecules begin to interact more efficiently, reactions occur faster, and feedback loops emerge. This is the first hint of a rudimentary metabolic system, a network of reactions that can sustain itself and adapt to changing conditions within the protocell. Some protocells acquire additional functions, incorporating molecules that stabilize membranes, improve replication, or facilitate chemical reactions. Interactions between protocells also occur, as molecules exchange between neighboring compartments, setting the stage for cooperation and competition at a molecular level. This dynamic interplay creates variation and drives early forms of natural selection, long before DNA or complex cells exist. Visualize the sheer diversity of these protocells. Some are tiny spheres, some elongated, some containing multiple compartments. Each variation represents a different experiment in organization, stability, and chemical efficiency. Over countless generations, the most robust configurations persist, gradually becoming more complex and capable of sustaining chemical processes for longer periods. External forces continue shaping their evolution. Meteorite impacts, lightning strikes, and fluctuating environmental conditions provide both challenges and opportunities. Protocells that can withstand these events survive, and in doing so, set the stage for even more sophisticated molecular systems. Imagine the resilience of these microscopic pioneers, surviving in harsh, dynamic environments, each one carrying the potential to unlock the next step toward life. These early protocells are also the first entities capable of compartmentalized replication. As molecules within a protocell replicate, the protocell itself can divide, passing some molecular components to its progeny. This is the earliest form of inheritance, a crucial principle that underlies all life. Picture a single protocell dividing, creating two microcosms, each carrying the echo of its chemical history forward into the future. Even in this microscopic world, the principles of evolution are quietly at work. Variation, replication, and environmental pressure create a system where complexity can accumulate. These protocells are not yet alive, not yet fully biological, but they are the crucibles in which life will eventually emerge, setting the stage for cells, organisms, and entire ecosystems. Floating among these protocells, one can imagine a universe buzzing with invisible experiments, each tiny droplet a microcosm of possibility. Here, the boundary between chemistry and biology begins to blur. Each protocell represents a critical step in the story of life, a fragile, transient form of organization that bridges molecular interactions and the emergence of biological systems billions of years later. Now, we move deeper into the unfolding story, from simple protocells to the first true cellular life forms. Picture a world of microscopic droplets, each containing a collection of molecules and chemical reactions, drifting in primordial pools or clinging to mineral surfaces. Among these protocells, some acquire increasingly sophisticated ways to manage internal chemistry, stabilize their membranes, and replicate more efficiently. Over millions of years, these tiny structures evolve into the earliest forms of cells, microscopic, self-sustaining units capable of harnessing energy, storing information, and reproducing. Internal organization becomes key. Within these early cells, molecules arrange into networks, catalyzing reactions in coordinated ways. Imagine molecules forming primitive metabolic pathways, extracting energy from their environment and using it to maintain stability. Chemical gradients across membranes allow energy storage, fueling reactions that produce essential building blocks. These first cells are remarkably resilient, able to survive fluctuations in temperature, chemical composition, and radiation while continuing to sustain lifelike processes inside their tiny boundaries. Replication becomes more sophisticated. While protocells divided through simple budding or splitting, early cells begin to refine mechanisms that ensure more consistent inheritance of molecular information. RNA molecules or precursors act as templates, guiding replication of essential components. Variations occur naturally, and those early cells capable of more accurate replication gain an advantage, slowly establishing the foundations of evolution. Picture generations of microscopic entities, each building upon the chemistry of its predecessors, gradually increasing in complexity and stability. The environment continues to shape cellular evolution. Shallow ponds, tidal pools, and hydrothermal vents provide diverse chemical landscapes. Some cells thrive in high-temperature vents, extracting energy from mineral-rich fluids. Others drift near sunlit surfaces, harnessing energy from radiation. This diversity of habitats drives adaptation, with certain features, membrane composition, metabolic strategies, replication fidelity selected for survival in specific conditions. The universe itself acts as a sculptor, shaping life through subtle pressures over vast timescales. Competition and cooperation emerge. Cells that can absorb nutrients efficiently, protect themselves from toxins, or share molecular components with neighbors gain advantages. Communities of early cells form, exchanging molecules or occupying different niches within the same environment. Even at this microscopic scale, the principles of ecology are visible, with interactions between individuals influencing survival and replication. Imagine microscopic networks of life, buzzing with interactions, exchanging resources, and subtly influencing each other's evolution. Mutations and chemical variation drive diversity. Mistakes in replication or changes in molecular pathways introduce differences between cells. Some variations prove advantageous, allowing cells to survive environmental stresses or exploit new resources. Others fail, disappearing from the population. This trial and error process gradually builds complexity, laying the groundwork for more sophisticated cellular mechanisms and eventually the emergence of true organisms. Energy management becomes increasingly refined. Early cells develop ways to capture energy efficiently from their surroundings, whether through chemical reactions, light absorption, or thermal gradients. This energy fuels the maintenance of internal order, replication of molecular components, and adaptation to changing conditions. Picture a microscopic world where each cell is a tiny energy processing unit, balancing intake and expenditure in delicate harmony with its environment. The emergence of membranes capable of selective transport marks a critical milestone. Cells begin to regulate what enters and exits, maintaining chemical gradients essential for lifelike processes. These membranes protect internal chemistry, allow resource accumulation, and facilitate interactions with the environment. With this step, cells become distinct entities, capable of maintaining internal organization over longer periods and increasing the likelihood of survival in varied environments. Over vast timescales, these early cells diversify. Some lineages experiment with different metabolic pathways. Others evolve structural innovations. Complex networks of interacting molecules form, leading to increasingly sophisticated life forms. The microscopic world is alive with experimentation, each cell a miniature laboratory, each interaction a step toward the complexity that will define biology across the universe. Floating among these first cells, one can imagine the quiet drama of life's emergence. Invisible to the naked eye, yet monumental in impact, these early cells represent the bridge between chemistry and biology, a turning point in the universe's history where self-sustaining, replicating systems arise, setting the stage for the diversity and complexity of life that will follow over billions of years. Now, imagine a world teeming with microscopic life, where the earliest cells have established themselves in a variety of environments, each facing unique challenges and opportunities. These cells are no longer uniform. They have begun to diversify. Some harness energy through chemical reactions, others through light absorption. Some develop thicker membranes to withstand extreme temperatures, while others float freely, exploiting abundant nutrients. This is a universe of experimentation, where the diversity of early life is shaped by both the environment and the subtle forces of chemistry. In shallow tidal pools, cells cluster together, forming primitive colonies. These aggregations offer advantages: protection from environmental stresses, sharing of resources, and increased efficiency in chemical interactions. Imagine thousands of cells cooperating in tiny clusters, each contributing to the stability and survival of the group. This is the first hint of social organization at a microscopic scale, a precursor to more complex life forms capable of division of labor and specialization. Meanwhile, other cells remain solitary, moving independently and exploring their environment. Some develop specialized adaptation structures to attach to surfaces, mechanisms to capture nutrients more efficiently, or primitive ways to sense environmental changes. This divergence of strategies fosters an evolutionary arms race at the microscopic level, where adaptability and innovation dictate which lineages survive and which fade into obscurity. Metabolic diversity expands dramatically during this period. Some cells evolve pathways to extract energy from chemical compounds in their surroundings, while others develop photosynthetic mechanisms to capture light. This division of metabolic labor allows ecosystems to become more complex, with different cells occupying specific ecological niches. Picture a microscopic landscape alive with interactions, chemical exchanges, and the dynamic ebb and flow of resources, each cell contributing to an invisible web of early life. Environmental pressures drive innovation. Fluctuating temperatures, changes in chemical composition, and the occasional impact from space deliver challenges that select for resilient and adaptable cells. Some lineages experiment with forming protective extracellular layers, others with internal storage mechanisms to survive periods of scarcity. Through countless generations, these pressures shape the architecture and behavior of early cellular life, promoting specialization and complexity. Chemical communication begins to emerge. Cells release signaling molecules that influence the behavior of neighbors, coordinating responses to environmental stimuli. These interactions lay the groundwork for cooperation, predation, and competition, establishing patterns that will become central to multicellular life. Imagine an invisible language evolving among cells, a subtle dialogue that orchestrates survival strategies and collective behavior. Gradually, cells explore the possibilities of combining into more complex arrangements. Some form chains, others develop primitive internal compartments, and a few experiment with specialization of internal processes. These innovations mark the earliest steps toward multicellularity, where division of labor and structural organization begin to emerge. It is a slow, tentative experimentation, a trial and error process that will, over millions of years, lead to the diversity of life we know today. In oxygen-poor environments, some cells evolve alternative metabolic strategies, creating localized ecosystems where chemical gradients sustain unique communities. These microenvironments become laboratories for evolutionary experimentation, producing novel adaptations and molecular innovations. Picture a universe alive with microscopic variation, where every cell is both an individual and a participant in a larger experimental system. Over vast expanses of time, these diverse cellular lineages interact, compete, and occasionally merge, giving rise to even more complex structures. Early predation and symbiosis emerge, forcing cells to develop defensive strategies, cooperative behaviors, and more efficient energy utilization. The microscopic world becomes a dynamic theater of life, with invisible dramas unfolding at every moment. Drifting through this ancient microscopic landscape, one can sense the immense creativity of nature at work. Diversity, adaptation, and interaction create the foundation for all future complexity, establishing the rules and patterns that will guide the evolution of multicellular organisms and eventually the incredible tapestry of life that spans our universe. One of the greatest puzzles hidden within the question, what was there before the universe, is the issue of time itself. Our everyday experiences are completely bound to time. We wake up in the morning, eat meals at certain hours, grow older as the days pass, and eventually watch the clock dictate the rhythm of our lives. Time feels so fundamental, so natural, that we rarely pause to consider whether it is something built into the fabric of existence, or something that emerged along with the universe itself. If time had a beginning, then asking what came before the universe may itself be a meaningless question. If time has always existed, then the universe may simply be one chapter in an endless cosmic story. This paradox lies at the heart of one of humanity's most profound mysteries. In physics, time is inseparably linked with space, forming the four-dimensional fabric we call space-time. When Albert Einstein developed his theory of general relativity in the early 20th century, he showed that time does not exist independently of the universe. Instead, it is woven together with space, stretching, warping, and curving under the influence of matter and energy. This realization changed everything. Time was no longer thought of as an infinite, absolute backdrop against which events occur. Instead, it became dynamic, influenced by the universe itself. This leads to a startling possibility. If the universe came into being, then space-time, space and time together may have been born with it. The Big Bang Theory suggests that 13.8 billion years ago, the universe began as a singularity, a point of infinite density and temperature. At that moment, space expanded outward, and time began to tick. But if time itself began with the Big Bang, then asking what happened before, it is like asking what's north of the North Pole. There may have simply been no before. The Big Bang was not just the creation of matter and energy, it was the creation of time itself. But many thinkers, both scientific and philosophical, are not satisfied with this answer. Human imagination struggles to accept a beginning without a cause. If time began at the Big Bang, what mechanism set it in motion? Was there something timeless that existed outside the universe, beyond our comprehension, that somehow initiated this event? Or does the concept of outside even make sense when talking about the universe as a whole? Some cosmologists have proposed that time might be more fundamental than we think. Perhaps the Big Bang was not the beginning of time, but a transition point in a much larger cosmic cycle. In this view, time stretches infinitely into the past, with the universe undergoing endless expansions and contractions, births and deaths. Each cycle erases traces of the previous one, but the flow of time never ceases. If this is true, then the Big Bang was not the first moment of existence, but just the most recent rebirth in a timeless sequence. On the other hand, certain modern theories suggest that time itself may not be fundamental at all. In quantum gravity research, some scientists argue that time is an emergent property, something that arises from deeper laws of physics, just as temperature emerges from the movement of countless particles. In this framework, time is not a basic ingredient of reality, but a phenomenon that only appears when systems become large and complex enough. If time is emergent, then before the universe there may have been a timeless state, something beyond human comprehension, where the concept of before or after has no meaning at all. Philosophers have wrestled with this problem for centuries. Saint Augustine, writing more than 1,600 years ago, famously reflected on the question, what was God doing before he created the world? His answer was that time itself was part of creation, and therefore there was no before. In modern philosophy, this line of reasoning still echoes. If time began with the universe, then the word before loses meaning. But the human mind struggles against this idea. We are so deeply embedded in time that it is almost impossible for us to imagine existence without it. There is also the notion of imaginary time, a concept proposed by physicist Stephen Hawking. In his work on the origins of the universe, Hawking suggested that near the Big Bang, time may not behave the way we expect. Instead of being linear, stretching from past to future, it may become curved, like a sphere. In this model, the beginning of the universe is like the South Pole. It is a boundary, but it does not require anything before. Just as there is nothing south of the South Pole, there may be nothing before the Big Bang. This idea offers a way to resolve the paradox, but it requires us to completely rethink what time is. Yet alternative perspectives exist. Some physicists believe the multiverse could solve the riddle of time's origin. In certain multiverse models, time extends infinitely, with our universe being just one bubble among countless others. The Big Bang would not mark the beginning of all time, but only the beginning of time inside our universe. Outside it or beyond it, time may stretch endlessly, encompassing the rise and fall of many universes. In this view, the question of what came before the universe is not meaningless at all, but rather an invitation to imagine a reality far larger than we can perceive. The problem of time reaches beyond physics into the realm of human perception. Our understanding of time is tied to change, memory, and anticipation. We measure time because we can recall the past and expect the future. If time itself did not exist before the universe, then there may have been no change, no process, no flow. But could such a state even be considered real? Or is reality itself inseparable from the passage of time? Some philosophers suggest that time is not just a dimension of the universe, but an essential feature of existence. Without time, there is no being. Others go even further, arguing that time is an illusion. According to this view, past, present, and future all exist simultaneously, and our experience of moving through time is a feature of human consciousness. If this is true, then asking what came before the universe may be the wrong question. There may be no before and after, only a vast, timeless reality in which the universe is one static configuration among many. These questions are not just abstract puzzles. They strike at the heart of our attempts to understand where we came from, and what reality itself is. If time began with the universe, then our cosmos has a definite origin, and all of existence is finite. If time is eternal, then our universe may be part of an infinite chain, stretching back without end. If time is emergent or illusory, then our most basic intuitions about reality may be profoundly wrong. Each possibility forces us to confront the limits of our imagination and the boundaries of human knowledge. And so, when we ask what was there before the universe, we are also asking what time is, how it functions, and whether it is as real as it feels. The problem of time remains one of the deepest mysteries in science and philosophy, a puzzle with no simple answers, only pathways that lead us further into wonder. When we speak of the beginning of everything, of the moment before time and space, of what might have existed before our universe came into being, one mysterious cosmic object seems to demand attention: black holes. They are not only strange anomalies of space-time, but also potential keys to understanding the very origins of existence. Some scientists speculate that black holes might hold the answer to what was there before the universe itself, linking collapse, rebirth, and the cycle of creation. Black holes are regions where gravity becomes so powerful that nothing, not even light, can escape. They are born from the death of massive stars, but some theories suggest their significance stretches far beyond the life cycle of stars. Within their event horizons lies the breakdown of the known laws of physics, leading to singularities, infinitely dense points where matter is crushed out of recognizable form. These singularities bear an eerie resemblance to the Big Bang singularity, the infinitely dense point from which the universe supposedly began. Could this be more than a coincidence? Could black holes represent not just the end of matter and energy, but the beginning of universes? The idea of black holes as cosmic bridges has gained traction in theoretical physics. The concept of a white hole, the opposite of a black hole, where matter and energy pour out rather than being consumed, suggests that what collapses into a black hole in one universe could emerge as a Big Bang in another. This radical idea paints black holes as portals, gateways to new realms of reality. If true, then perhaps before our universe began, it was born out of the collapse of a massive star in a previous cosmos, exploding into being as our Big Bang through the other side of a black hole. This leads to the black hole cosmology hypothesis, sometimes referred to as the fecund universes theory. It suggests that every black hole spawns a new universe, each with its own physical constants, laws, and structure. If our universe is the child of another, then the black holes within our own cosmos may themselves be giving birth to countless new universes, branching into an endless family tree of reality. In this picture, what came before the universe is not nothingness, but a cycle of universes continuously creating new offspring through the mysterious process of gravitational collapse. Another perspective emerges from the mathematics of loop quantum gravity, a theory that seeks to unite quantum mechanics and general relativity. Instead of singularities being infinitely dense points, they might be bounces. In this model, when matter falls into a black hole, it compresses to a finite, incredibly small size, then rebounds outward. This rebound could seed the formation of a new universe. In that sense, the singularity that we associate with the Big Bang could have been the bounce of matter and energy from a black hole in a pre-existing universe. What we call the beginning may simply have been a continuation, a recycling of reality from one state into another. Even more fascinating is the possibility that the information consumed by black holes, the very data about particles, energy and matter, does not vanish as once thought, but remains encoded in some way. The black hole information paradox, explored by physicists like Stephen Hawking, touches on this mystery. If information is preserved rather than destroyed, then perhaps the seeds of our universe were encoded within the collapse of a black hole in a prior cosmos. What we are and everything we see around us may be the re-expression of information carried through cosmic collapse into cosmic birth. But black holes are not only scientific puzzles, they are also evocative symbols in human imagination. Across cultures, they are likened to voids, abysses, and gateways to other realms. In ancient mythology, the idea of the underworld, of descending into darkness to find renewal or transformation, resonates with the way black holes consume and possibly regenerate the universe. Some thinkers even suggest that myths of cosmic eggs, or worlds emerging from chaos, reflect an ancient, intuitive understanding of cycles, similar to those seen in black hole cosmology. The speculative edge of physics pushes this further. Some propose that the universe itself could be the inside of a black hole. In this model, what we experience as space-time expansion, the ongoing growth of the cosmos since the Big Bang, is simply the stretching of space inside a black hole formed in another universe. Our universe would then be one of countless others hidden inside the fabric of these cosmic behemoths, like bubbles contained within bubbles. So, when we ask what was there before the universe, black holes stand as one of the most compelling answers. They challenge our concepts of beginning and end, suggesting that perhaps there is no ultimate starting point, but rather a chain of creation where every collapse leads to a new birth. If our universe did indeed emerge from the depths of a black hole, then the true mystery is not just what came before, but how many times this cycle has occurred, and how many universes may lie beyond our perception. When we ask what existed before the universe, we often picture vast expanses of darkness, or a silent void waiting to be filled. But quantum physics turns that vision inside out. In its framework, emptiness is never truly empty. What we call nothing is alive with possibility. A restless ocean of energy and fluctuations that cannot be silenced. Before stars, before galaxies, before even space and time itself, there may have been a quantum froth, an invisible landscape bubbling with particles that flash in and out of existence. These are the quantum fluctuations, ephemeral, unpredictable, yet carrying the seeds of everything. To imagine this pre-cosmic state, think of a seething cauldron where particles are constantly appearing, annihilating, and reappearing, not because of any cause, but because uncertainty itself demands it. This is not a familiar kind of creation. It is not an artist painting on a canvas, or a builder laying bricks. Instead, it is a restless background, a mathematical necessity of the laws we now see in quantum mechanics. The Heisenberg uncertainty principle does not allow complete stillness. Even when there seems to be nothing, there is always a whisper, a jitter, a potential waiting to unfold. Physicists sometimes describe this as the quantum vacuum. But the word vacuum is misleading. It sounds like a clean, hollow space, but the quantum vacuum is a storm. Imagine a field where invisible waves ripple and collide. These waves give birth to particles, tiny bursts of energy that exist for a blink and then vanish. They are called virtual particles, yet their effects are real. They shape the universe we see today. From this invisible soup may have come the first spark that ignited the Big Bang. The idea is bold because it suggests that before the universe there was no need for external cause. Instead, the universe could be a natural outgrowth of quantum law. Stephen Hawking once pointed to this, arguing that when you combine quantum mechanics with the theory of relativity, the universe could spontaneously emerge without requiring a designer or a prior trigger. Time itself could curve back, smoothing into a state where asking before loses meaning. Yet the haunting thought remains. If the universe can rise from quantum nothingness, why is there such a law at all? Why does quantum possibility exist in the first place? Within this framework, the birth of the cosmos may have been like a bubble appearing in boiling water. One moment the vacuum seethed invisibly. The next, a bubble of space-time emerged. That bubble inflated, stretching faster than the speed of light, smoothing irregularities, and shaping the cosmos into the vast structure we see now. Inflation theory links directly with these quantum seeds. The tiny fluctuations inside that bubble were stretched across the universe, becoming the patterns that later formed galaxies, clusters, and cosmic web filaments. The stars we look at today trace their ancestry back to those infinitesimal whispers of quantum foam. But if we stop here, we still face a mystery. The quantum vacuum is not nothing, it is something. It is governed by laws, equations, symmetries. So perhaps what existed before the universe was not a void, but an eternal framework of physics itself. A set of timeless rules etched deeper than matter, deeper than energy, guiding the dance of possibility. This raises yet another unsettling question. Are these laws necessary truths, existing beyond the universe? Or are they contingent, like a local custom in one reality among countless others? If universes can bubble from quantum froth, perhaps there are infinitely many, each with its own variation of rules. This vision of before becomes stranger the longer you gaze at it. Instead of a silent void, you encounter a restless stage, a cosmic roulette wheel spinning endlessly. What we see as a single Big Bang might be only one outcome among infinite roles. The strange thing about quantum theory is that it resists certainty. It does not say what must happen, only what might happen, weighted by probability. If the birth of the universe was quantum in nature, then its existence is not a necessity, it is a chance. A probability that turned out in our favor, giving rise to stars, planets, and eventually to beings capable of asking this very question. And still, the mind resists. How can chance exist without time to unfold? How can there be fluctuation if there is no background to fluctuate against? In a way, this paradox lies at the heart of human thought about origins. We imagine beginnings as events in time. But if time itself is a byproduct of the universe, then the word before becomes slippery. The quantum froth might not have happened before the universe. Instead, it might have been the canvas upon which time itself was painted. A realm that exists outside chronology, where possibility does not flow in sequence but simply is. When we ask what was there before the universe, one of the boldest ideas that arises is the possibility that our universe is not a unique or singular event, but part of an endless chain of creation and destruction. This concept is known as the cyclical universe theory, an idea that stretches across science, philosophy, and even ancient mythologies. Rather than imagining a clear beginning or a final end, this view proposes that universes are born, expand, evolve, collapse, and then give rise to new universes in an eternal rhythm. To understand this, we must step beyond the comfort of linear time and imagine existence as a never-ending pulse, like the beating of a cosmic heart. The idea of cycles is not new. Ancient Hindu philosophy describes the cosmic cycles of creation and destruction, known as kalpas. In this vision, universes arise, endure for unimaginable spans of time, and eventually dissolve back into nothingness, only to be reborn again. This framework does not place ultimate importance on a single beginning, but rather emphasizes continuity, flow, and regeneration. Similarly, ancient Greek philosophers like Heraclitus believed in eternal recurrence, where all things return in cycles, endlessly repeating in different forms. These mythological and philosophical models surprisingly mirror what some modern physicists have dared to suggest, that the universe itself may undergo infinite rebirths. In modern cosmology, this concept takes shape in several forms. One is the Big Bounce theory. Instead of the universe beginning from a singular Big Bang, the Big Bounce proposes that what we call the Big Bang was simply the latest bounce, in an eternal sequence of expansions and contractions. According to this model, the universe could eventually stop expanding, reverse its course, collapse under its own gravity, and shrink into an incredibly dense state. From that collapse, conditions would reset, triggering another Big Bang-like explosion, starting the cycle anew. What we see as our universe may therefore be just one chapter in an infinite story of births, deaths, and rebirths. Another fascinating variation is the idea of conformal cyclic cosmology, proposed by physicist Roger Penrose. In this theory, universes follow one after another in what he calls eons. When a universe expands so vastly that matter and energy become diluted into near uniformity, time and space themselves lose distinction, setting the stage for a new Big Bang to arise. In this model, there is no final ending, only transitions from one eon to the next. It is as if universes are pearls on an infinite string, each shining for a time before fading into the background and giving way to another. If we consider cycles deeply, they resonate with the natural patterns we see all around us. Stars are born, live their lives, and die, often scattering the very elements that will later form new stars and planets. Seasons follow one another in endless sequence. Life itself emerges, perishes, and regenerates. The idea that the universe might also follow such a rhythm gives cosmic significance to the cycles we already observe. It implies that destruction is not an ultimate ending but a necessary part of renewal. The collapse of one universe may simply plant the seed for the next. But this concept also raises profound questions. If universes arise endlessly, does each cycle repeat exactly the same way, with the same galaxies, stars, and beings? Or does each iteration generate new and unpredictable forms of existence? Could we be living lives that have been lived countless times before, in endless recurrence? Or are we part of a universe that will never repeat itself, that constantly reinvents the possibilities of existence? The answers are as elusive as the cycles themselves, yet they hint at the profound interconnectedness between what we call beginnings and endings. Even within this cyclical framework, there remains the mystery of time itself. If the universe has always existed in cycles, then the notion of a first cause disappears. There is no single origin to point toward, no ultimate moment of creation to discover. Instead, there is only an eternal unfolding, without beginning or end. In this vision, the question, what was there before the universe, becomes inseparable from the rhythm of existence itself. Perhaps there was never a true before, only an infinite sequence of transformations, each giving rise to the next in a cosmic dance that never stops. The cyclical universe theory offers us a breathtaking vision, one where the universe is not fragile or finite, but endlessly resilient. It refuses to give in to the idea of an ultimate end or a singular beginning. Instead, it portrays existence as a vast, eternal cycle, echoing through infinite time, with every collapse followed by a rebirth, and every ending paving the way for a new dawn of creation. When we ponder what existed before the universe, one of the most provocative ideas in modern physics is the concept of the multiverse. Instead of a single isolated universe, there may be an infinite collection of universes, each with its own physical laws, dimensions, and histories. Some universes might resemble ours closely, while others are completely alien, governed by forces we cannot even imagine. In this framework, what came before our universe might not be a singular nothingness, but a boundless ocean of other universes, each arising, existing, and fading in ways that could stretch beyond comprehension. There are several multiverse theories, each grounded in different scientific reasoning. One is the inflationary multiverse. According to this idea, the rapid expansion of space during the earliest moments of cosmic inflation did not occur uniformly. Instead, patches of space inflated at slightly different rates, forming bubble-like universes with varying properties. Our universe would then be one of countless bubbles floating in a vast cosmic foam. Before the birth of our own universe, this multiverse may have already existed, teeming with countless other realities. It is a staggering vision. A realm where universes are constantly forming, with different constants, dimensions, and physical laws, shaping the possibilities of existence in each. Another perspective comes from string theory, which posits that the fundamental building blocks of reality are not particles but tiny, vibrating strings. These strings can exist in multiple dimensions, potentially giving rise to countless universes with different vibrational patterns. Some physicists suggest that every possible configuration of strings produces a unique universe. This leads to the idea of the string landscape, a virtually infinite array of universes, each with its own laws and constants. In this context, our universe is just one realization of an unimaginably vast cosmic experiment. Before our universe, there could have been countless others, each emerging from the vibrational possibilities of strings in higher dimensional space. The multiverse idea also intersects with the many-worlds interpretation of quantum mechanics. This interpretation proposes that every time a quantum event occurs with multiple possible outcomes, the universe splits into parallel realities, each realizing one of the outcomes. Applied to the birth of the universe itself, it suggests that every possible version of the cosmos exists simultaneously. Before our universe emerged, countless other universes may have existed or continue to exist alongside it, differing in ways both subtle and profound. In this framework, there is no singular before, only a sprawling web of realities extending infinitely in all directions. Some scientists have even proposed that these parallel universes might occasionally interact. Hypothetical events like brain collisions in higher dimensional space could trigger the birth of a new universe, including our own. In this vision, the Big Bang is not the ultimate beginning, but the result of a cosmic interaction, a ripple or impact between universes in a higher dimensional space. What existed before the universe, in this case, is the dynamic and ever-shifting multiverse, a stage upon which countless creations are continuously unfolding. The implications are mind-bending. If parallel universes exist, then every possibility, no matter how improbable, is realized somewhere. Somewhere out there, a universe exists in which our solar system never formed, or where life evolved in completely unimaginable ways. Somewhere else, physical laws may allow for faster-than-light travel, infinite energy, or forms of existence beyond comprehension. The idea that the universe we inhabit is just one of many invites a humbling perspective. Our reality is just a tiny thread woven into an infinite cosmic tapestry. Even more fascinating is the philosophical dimension of the multiverse. It suggests that our universe is not the product of chance alone, but one manifestation among many possibilities. It raises questions about meaning, uniqueness, and the nature of existence itself. If countless universes exist, are we merely witnessing one version of reality? Does the multiverse provide a natural explanation for why the physical constants of our universe appear so finely tuned to allow life? Perhaps before our universe existed, there was no single template, only a field of infinite potential, in which countless universes were waiting to emerge, each exploring different outcomes of physical law. Some cosmologists propose that the multiverse may also operate under its own cycles. Universes may be born, expand, collide, and fade away, interacting in subtle, unseen ways. In this context, before our universe, there may have been a vast playground of other universes, each with histories, structures, and lifespans beyond anything we can imagine. The multiverse becomes not just a collection of worlds, but a cosmic ecosystem where creation, evolution, and destruction occur on scales that dwarf human comprehension. This perspective also challenges the very concept of origin. If countless universes have already existed, or are existing simultaneously, then the question of what came before the universe may be meaningless in traditional terms. There is no singular starting point, no linear timeline. Instead, there is a sprawling, branching web of realities where beginnings and endings are fluid. And the universe we see is merely one node in an infinite network of possibilities. Even without direct evidence, the multiverse invites curiosity, wonder, and speculation. It pushes the boundaries of human imagination, forcing us to consider realities that defy the familiar rules of physics, space, and time. The vision of an infinite multiverse paints a cosmos that is far richer and stranger than any single universe could contain, offering a framework where the four becomes not a question of emptiness, but a question of infinite potential, endlessly unfolding across countless dimensions. Thanks for watching. Tonight, we travel to the edges of imagination, peering into mysteries beyond time and space. And if your mind is still buzzing with possibilities, that's exactly where it should be. If this journey sparked your curiosity, check out our other videos, where more stories of history, science, and the unknown await, ready to sweep you into worlds both strange and familiar. Share your thoughts in the comments or let us know where you're joining from, as we continue to explore together. Keep wondering, keep imagining, and let each story carry you further than you ever thought possible.